we're doing a deep energy retrofit to a 59-unit townhouse complex here in Edmonton. And the thrust behind it is the serious situation that we're in. So everybody knows that we need to reduce our GHGs to almost nothing by 2050, which is in itself pretty scary. But buildings are responsible for about 40% of current total greenhouse gases, and everything else is kind of the rest. The problem is that 70 to 80% of the buildings that we'll be using in 2050 when we need to be carbon neutral are already built. If we don't figure out a way to tackle those existing buildings, we're pretty much in trouble. Like, that's almost a third of greenhouse gases that don't get touched, and that adds up to basically a disaster scenario for our kids and the planet. So the Dutch have a pretty good start on this. They've got a way forward. They've developed a system whereby they make panels in an offsite factory that come to the building, to existing buildings, and make them net zero ready very quickly in a matter of weeks. And they've so far done about 5,000 units. They've got another 10,000 in the works, and their pilot project is about 110,000 units, and after that, they are anticipating millions. So this is very inspiring, and is the starting point for the Sundance Housing Co-op project. So this started with some students who wanted an energy efficiency related project for their capstone project, their Bachelor of Technology capstone project. And I suggested to them a deep energy retrofit of the Sundance Housing Co-op where I used to live, and which is just across my back fence. And that's what they did. They did a great job of it. We blower door tested a bunch of units. They did energy audits on a sample and got pricing and presented it to the co-op. And then it sort of stopped but the co-op was interested. So they hired Renew Engineering to sort of professionalize the study. And Stuart Fix from Renew presented them with a number of alternatives, including costing. He did the modeling in IES. And the co-op was fairly interesting, but the overall price tag was about $5 million. And so that was a major hurdle. And this is a challenging site. In the Netherlands, the buildings tend to be simple and not too much landscaping around them, where we've got these 59-unit townhousing, 15 buildings in all, and mature landscaping, fences that are close to them, sheds, concrete up against the buildings, cantilevers. We've got some pretty tight little jogs and member-built additions, utility connections, all kinds of complications. In fact, I got a tour of a couple of Energiesproung sites in Holland with somebody from the Energiesproung nonprofit. And when I showed him these pictures, he said, "Oh, that would be a no-go." But we're committed to this, and we think one of the contributions that this project has to make is a library of how to deal with these kinds of situations, because none of them are that uncommon. So in essence, the advantages of panelized deep energy retrofits are, superb quality, in controlled settings. The finished buildings are healthier, very, very comfortable, long-term sustainable. Basically, we're cutting the energy loads by about 75%. It's a one-time solution that looks after everything. You end up with a building that's got a very long life because it's been detailed with modern building science. It's new cladding, new windows, and put together in a fairly quickly and much more affordable in total. And so one of the sort of enemies of deep energy retrofits that we've noticed in other buildings that we've worked on and looked at is half measures. Basically, somebody will put in a somewhat better window, but they won't deal with air tightness. They may reside the building and add an inch or an inch and a half of insulation under the siding, again, without looking at airtightness or doing the windows and how they all fit together. It's way cheaper in the long run if you do all of this at once in a full system that looks after everything. Everything fits together and works, and in lots of cases it will make more sense to wait until the owner can afford to do the whole thing in one shot. Otherwise, it will likely never get done. In the midst of the discussions about this project, we became aware of an opportunity for some Government of Canada R&D funding that was targeted at exactly this kind of project. And we were successful in getting that. They liked the project and the capability that they perceived in the team, and essentially funding this what's now a $5.3 million project to the tune of about $2.5 million. So that really took any question about affordability away from the co-op. They were already kind of struggling with the idea of spending $5 million on a 30-year payback. So with this federal funding, it made it relatively easy to make the leap. The overall process for a panelized deep energy retrofit involves the digital capture of the existing building, and this is we didn't do this in the pilot phase. In the pilot phase, we actually we're just doing one building, the one in the picture here, and we got those measurements via a tape measure because we haven't gotten the photogrammetry to work to the precision that we need yet. And we're also experimenting with LiDAR, laser scanning, on the next building. So this is still a work in progress. We're getting closer, but we haven't got it down yet. But when we scale this up to the other 57 units, it will be absolutely essential to get at the precision we need. We think that precision is around 4 to 5 millimeters. Tape measurements are just not reliable. We double and triple checked our measurements in this instance because we had no alternative. But when you're out there with a clipboard and a measuring tape, you get back to the office and wonder, was that window on that side of the house, or where was that vent? Either you go back and check and be absolutely sure, or the consequences could be very expensive. I mean, imagine you get panels built off-site there with a crew of 6 and a crane, and the siding is on the panel, windows are in, it's basically finished, and then you find that a window is 2 inches off where it's supposed to be. The consequences are extremely costly, and so getting the digital capture accurate is very important. And the same goes for taking the digital capture to dimensions panel drawings. Again, these are being built in a factory off-site. There's no ability to check or answer questions. They just have to be right. And so taking the digital capture and turning that into a finished panel drawing is also critical. So in the pilot, on the first duplex, we have a number of details. We thought it through quite very carefully, but we actually built the panels on site, in fact, on my driveway, and rather than building them off site. And so we built them, stood them, installed the windows, put on the siding, the water-resistant barrier that's also our airtight layer. We wanted to be sure before we got somebody else manufacturing them that we had the details right, that the basic conception was going to work, and basically we did. We're very satisfied with that. We're not satisfied with how long it took us, but the general scheme is that we start with a treated plywood box beam that goes partly into the ground that carries the panel weight, install the panels on top of that, and then fill the wall cavity with cellulose from the top. And all of that worked reasonably well. We dug around the foundation and installed 6 inches of EPS below the box beam. That was digging it with a backhoe was a mistake. After 50 years in the construction business, I will never, ever get used to how much dirt any hole ever leaves. We had dirt everywhere. We trashed the landscaping. It was a disaster. And as we go forward, we're going to use a hydrovac truck to make a trench just big enough for the foam insulation that will be insulating the basements. And then once the box beam was on and the panels built, we swung them in place. That was super fun and went about as expected. And we also built roof sections. We basically a new scissor truss roof, which you'll see in a section in a moment, that were swung up into bunches to build a new roof over the top. Here's the new building section. We wrapped the top of the existing roof with 6 mil poly vapor barrier, well sealed, wrapped over the old gable ends, and ready to seal to the outside water resistant barrier on the panels. And the material that we used is a material from Casella Dorkin called Delta Vent S. It's a vapor open, very vapor open, roughly 70 perms, airtight, water-resistant barrier. So our whole airtightness strategy relies on this. The existing building has a 4 mil poly vapor barrier that is very pretty sketchy. Basically, we air tested the building before we started, and one unit had an air change rate at 50 pascals of 6 per hour, and the other was 7. This includes the leakage through the existing open B-vent type chimneys. But we're targeting around 0.7 air changes an hour. We're going to do our air tightness test next week. The new windows are fiberglass framed, center glass 8.3 R value with relatively good frames, R5, and set back into the wall. We're getting an effective R28 of new insulation. Our estimate of the original insulation in the 2x6 wall is about R15. So we get a total of about R43. And then we're adding R50 cellulose on top of the new vapor barrier over the old shingles. So one of the advantages of this system is we're doing the whole thing over top of the existing building. We take off minimal amount of siding, only where we need to make connections, and leave the shingles on, basically take the old overhangs off, and we're ready to go. And we had to remove and replace the porches. So these are some of our air and water sealing details. You can see the Delta Vent S material, the taped sort of U-shaped things are sealing up holes that we needed to leave to and use to make sure that we had the full density in our cellulose. And we left the siding off at the joints between the panels so that we could make occasionally so we could get the cellulose in, but also so that we could seal those laps and be sure that we were going to get the air tightness we needed. We had some complications over on the left here with the sealing around the old cantilever and also holding up carrying the weight of the panel, but we devised a block using structural screws and pieces of LVL material and 3/4 inch plywood that worked reasonably well for that. We set the windows back into the wall to keep the inside face of the glass warm enough to reduce and almost eliminate condensation. So that's always a complex undertaking, fairly labor intensive and requiring good care and attention. We've actually worked out a few refinements of this that will be in the set of drawings that I send you. But by and large, this all worked out fairly well. We also, in order to minimize the amount of time we were in people's houses doing the window extensions, we screwed alignment strips that were carefully indexed to the window frame so that when we made the window return boxes, we could just slide them in, screw them into those alignment strips, and throw the casing on and a little batten strip to cover the gap. That worked fairly well, and we'll continue to do that. Because we've made the buildings really airtight, we've of course had to put in HRVs. That was a bit of a challenge. We ended up having to find pathways in existing walls so that we could get pickups in the kitchen and the second floor bathroom. We're using the existing furnace ductwork to distribute the fresh air. Running supply ducts would be far too disruptive and time-consuming and expensive. We've used this strategy for about 30 years and gotten excellent air quality with it. It was tricky to find exterior pathways to get to exhaust the stale air and bring in fresh air, but we think we've got that managed. It actually isn't under the porch as this looks. And these are some specs. This can go with. I won't actually read these off, but they're there just to give you an idea of where we got to. Our intent with this project is that we will also electrify the whole site. So currently, these buildings run on natural gas, but after the retrofit, the loads will be so small that the fixed monthly cost of just having a meter adds up to about $650 per year per unit, will be far more than the minuscule amount of gas that's going through it. And ultimately, for sustainability in the long run, we have to stop using fossil fuels. And the co-op is taking the long view, and they're also realizing how expensive this is and what an opportunity it is, and they want to do it once and once only. Part of our project will be to replace all the furnaces with air source heat pumps. One of the problems we've run into is that the current electrical service for each of these units is only 60 amps. We need at least 100 amps to run air source heat pumps and air source heat pump hot water tanks. So we're currently doing an engineering study to explore to find the lowest cost solution to upgrading the electricity on the site. It's going to mean running additional underground lines to more than half of the units and some upgrades to the panels. So it is possible that we'll go ahead with this and do only the energy upgrade and leave the gas, but I'm really hoping not. We should know that in the next few weeks. Getting the opportunity to do this, and in fact, it's an impediment for us to actually work around these gas-heated buildings. The gas meters are in the way. The gas meters are a penetration in the envelope. We've got open B-vent chimneys on some units. We've got open B-vent chimneys that are still there for the hot water tanks, which are old, and the furnaces have been replaced with condensing furnaces, so they've got an additional chimney out the side. Plus, they all have combustion air outlets. And when we did the pilot, we spent a fair bit of time fooling around with those and extending the B-vents. And now when we electrify, we're going to have to go back and take those things out and seal and patch those holes. So we really want to avoid that, but it is possible that this is going to delay us because we have to get the electrical upgrade done first. So costs are pretty frightening on this. In our proposal to the co-op and to Enercan, we broke the project into two phases. The first phase is to retrofit the 2 units that we've already done, and the second phase is to do the other 57. Our budget for the first 2 units was $120,000 a unit. That's about where the cost came in. And we made lots of mistakes. We have a list, no kidding, of 200 items that we need to do better or different when it comes to the pilot. Some of them are pretty simple, some of them not so much. But in order to go ahead with the other 57 units, we need to bring the cost down to about $85,000 a unit. And that's going to have to come from the advantages of offsite panelization, although the offsite panelization comes with a built-in cost of the facility to build the panels and also the trucking costs. So it's not a huge win. It's a big deal in time. We've got a number of potential suppliers of panels, and we're negotiating with people to make sure they can meet our specifications and our budget. And then we're also anticipating that we will get better at this as we go. We made lots of mistakes that we won't make again, and that will reduce our costs as well. And we have an advantage also in that the pilot was a duplex. It has only one party wall. On average, our buildings are 4 units each, so we have more party walls and fewer panels per unit. But our first cut at this, that getting down to that $85,000 per unit is going to be a challenge. So this is a very people intensive process. When I first started researching Energiesproung, I was puzzled that I was looking for building science studies, construction details, and that kind of thing. And I found that mostly what I was there were pictures of people talking to each other, which, as I say, was puzzling. And now I understand that better. We're dealing with a democratic housing co-op. They have wonderful processes, but everybody has a say. And the input from all of those people is very rich, but it's also very, very time consuming. And some people in the co-op are thrilled and proud of the contribution that they're making to moving the needle on this critical issue. And some people, not so much. They really just don't want to be bothered. They just want to get on with their lives. And I got this reinforced on my tour in the Netherlands as well. So it's really critical that we persuade people to buy into this and to trust us. I mean, we're working in their houses, and that we minimize the amount of disruption and the time that we spend in their houses. On our pilot, we had people who were really enthusiastic about it, very relaxed. It was such a good thing because we were in and out of there so many times. In the Netherlands, I think they try to keep that to a week. It may take 3 weeks to do the whole group of townhouses, but from the day that they walk in your door to the day they walk out with the paint drying is like a week. And that's, we've learned that lesson. We're tightening our processes up. But you also have to, to get buy-in for this, you have to make life better. And so the wonderful, warm, comfortable, high-quality indoor air quality is one thing, but somehow you have to kind of make them nicer too. And we think the box bay windows that we put on the south side are one way to do that. They're beautiful window seats, and really every window becomes a deep windowsill. We've also, in the course of rebuilding the porches, installed skylights. So anything we can do along the way that doesn't cost too much to make people like their houses better will help this all in the long run. And so the finished product looks like this. You can see the skylights in the porches there, and the box bay windows, and our next victim over there on the right with the photogrammetry targets. So I think I'll end it there. I could go on for days on this. This is multifaceted. There are so many aspects and so much to learn at every tier. And by way of learning, we're in the process of starting a nonprofit called Retrofit Canada. And our intention is that this will become an information library for doing this, so that people starting to do this stuff can start with new mistakes and avoid the ones that we've already made. We're going to put all of our cost information, our building details, everything that we can from this project, and encourage similar projects to do the same thing on this website.
Excellent.
Thanks very much.
Excellent. Thank you, Peter.